heat balance. That's the topic for today. Now, the purpose of heat balance is to give you an account of how the heat energy that will be supplied from the fuel through combustion is disposed of on its passage through an engine. In order to draw up a heat balance sheet for an engine, we will need to conduct a complete test on the engine with the engine running at a constant load. Now, the brake power, the fuel consumption, and its calorific value, and the mass of water circulating through the cooling jackets, together with its inlet and outlet temperatures, must be measured. Remember that the mass of the exhaust gases can be obtained by adding mass of exhaust gases together the mass of the fuel supplied and the mass of the air supplied. So mass of the fuel that will be supplied and the mass of the air supplied. The latter being measured by means of an orifice, or we can equally calculate it from an analysis of the exhaust gases. Now, with all the data that we will accumulate through the test that we conducted on the engine at constant load, we can do some calculations as follows. Remember, what we are interested in is to gather all this data: the brake power, the fuel consumption, the calorific value of the fuel, the mass of circulating water through coolant jackets, inlet and outlet temperatures, the mass and temperature of exhaust gases. When we get all this data available through the test on the engine at constant load, then we will be able to draw up a heat balance sheet, which is basically an account of how the heat energy supply from the fuel through combustion is being used or get rid of on its passage through an engine. Remember that the mass of the exhaust gases equal to the mass of fuel supplied plus the mass of the air supplied. Now, for us to be able to do the calculations, we should be able to understand these conversions. The heat supply from the fuel per minute is equal to the mass of the fuel used per minute times the calorific value. Now, if you want to know the work that is being done by the engine per minute, then we should be able to multiply the brake power by 60. Remember that the brake power is expressed in watts, which is basically for power, so it's joules per second. So for us to be able to convert the useful work to useful work per minute, we multiply by 60, which is basically 60 seconds, so that we can convert the power unit, which was in joules per second, into joules per minute. Now, the heat to cooling water per minute can be arrived at by taking the product of the mass of water per minute times the specific heat capacity times the temperature rise. The heat to exhaust per minute is also equal to the mass of the exhaust per minute times the specific heat capacity times the temperature rise. Alternatively, when the exhaust heat is measured by passing it through a water-cooled manifold or exhaust gas calorimeter, we can calculate the heat to exhaust per minute to be as the mass of water per minute times the specific heat capacity times the temperature rise. Note the difference. Earlier, I said the heat to exhaust per minute is the mass of exhaust per minute times the specific heat capacity times the temperature rise. The difference between this and this is basically the mass of exhaust per minute and then the mass of water per minute. Here we are taking the mass of exhaust per minute because we can be able to derive that. But when it is difficult for us to derive this, then we pass the exhaust gas through an exhaust gas calorimeter, and then the heat that will be transferred to the water in the calorimeter will now be the same as the heat that the exhaust gas was having. Good. Now the heat to the surroundings per minute is equal to the heat supplied from the fuel minus the sum of the heat to useful work per minute, the heat to cooling water per minute, then the heat to exhaust gases per minute. So you will notice that in all, we have 5 places that the heat energy, which was derived from burning the fuel, get expended. Some got to useful work, some got to do work, that is at the output shaft, which we'll record as our brake power. Some of that heat energy is lost through the exhaust gas. Some also got lost to the surrounding through radiation. Some got lost through the cooling water. Good. So these four major ways are the ways by which the heat energy which was produced from the burning of the fuel gets to be used. Mostly, the one that got to do useful work is about 1/3 of the total. So about 2/3 goes to waste through this means: the exhaust, surroundings, and then cooling water. That is why in some technologies, as in the turbocharger technology, they try to harness the heat that will be lost through the exhaust gas to power the turbocharger, which in turn also supplies enough air at some particular pressure so that we fill in the cylinder, then producing a higher volumetric efficiency for the engine. And this also results in a higher thermal efficiency. For this to make a little bit of sense to you, I would suggest we take an example and then solve it together. During a test, an engine had a fuel consumption rate of 12 kilograms per hour, whilst developing 45 kilowatts. The air-fuel ratio by mass being 25:1, and the calorific value of the fuel was 45 megajoules per kilogram. Now, cooling water circulated through the cooling jacket at a rate of 25 kilograms per minute and had temperature rise of 8 degrees Celsius. Air and fuel entered the cylinders at 32 degrees Celsius through the inlet manifold, and exhaust gases left the cylinders at 560 degrees Celsius through the exhaust manifold. Now, our job is to make an account of how the heat energy produced from burning the fuel gets to be expended. So we have to draw up a heat balance for this test. Then we express each item in terms of megajoules per minute and also in percentage of the heat supplied to the engine. We were given specific heat capacities of water and exhaust gases as 4.2 kilojoules per kilogram degree Celsius and 1.05 kilojoules per kilogram degree Celsius respectively. So as a result of conducting the test on the engine, we got these as our data that we're going to use to be able to draw up an account of how the heat energy produced from burning the fuel got used. Now, the first and foremost is for us to know how much energy was produced in the cylinder. So for us to know that, it's as a result of burning the fuel in the cylinder. So we need to account for the heat energy produced from what? The fuel per minute. To do that, the fuel was flowing at a rate of 12 kilograms per minute. So we have 12 kilograms per 60 minutes. We multiply that by 45 megajoules per kilogram, which is the calorific value of the fuel. The result is 9 megajoules per minute. Now, the heat that was used to do useful work per minute, that's the heat that was able to produce work at the output shaft per minute, is 45 multiplying 10 power 3 multiplying 60 over 10 power 6. I did all the conversions over here so that there won't be any need for us writing a lot of units, and the final unit to be megajoules per minute. The result we'll get is 2.7 megajoules per minute. All that was needed was provided in the question. So there shouldn't be any difficulty in doing this, because I provided the relationship between all the items that are needed to draw the heat balance and how they are arrived at. So if you have this at hand, then you'll easily be able to work through it. Now, the heat to cooling water per minute is 75 kilograms per minute. That's the flow rate times 4.2 megajoules. So this is like the mass flow rate times the specific heat capacity times the temperature rise. That will give us an answer of 2.52 megajoules per minute. Now, for us to be able to calculate the heat to exhaust, we were given not the mass of exhaust gases, unlike how we're given the mass of the cooling water. So we're just able to put it in and then work through it. So now we have to derive it by ourselves. Now, how do we do it? So to know the mass of exhaust gas, we must know the mass of fuel and know the mass of what? The air. So the mass of air used per minute is equal to the mass of fuel used per minute times the air-fuel ratio. This is basically derived from the air-fuel ratio formula, where air-fuel ratio was equal to the mass of air over the mass of fuel. And what we did over here was basically just multiplication through by the mass of fuel, so that we can get the mass of air. So the mass of air used per minute was 5 kilograms per minute. Then the mass of exhaust gases flowing per minute now will be equal to the mass of fuel used per minute, which we've just calculated. Sorry, the mass of fuel used per minute, which we'll be calculating, plus the mass of air used per minute, which we've just calculated. So the 12 kilograms over 60 minutes was the mass of fuel used per minute. We use it once here. Yep. And then we add the 5 kilograms per minute to it. So now this gives us a total composition of the exhaust gases that were flowing through per minute. And the result was 5.2 kilograms per minute. Now, knowing the mass of exhaust gases, then we can calculate the heat energy to exhaust per minute by multiplying the flow rate of the exhaust gas the mass flow rate of the exhaust gas times the specific heat capacity of the exhaust gas ending the temperature rise. The temperature rise of the exhaust gas is as a result of the temperature of the exhaust gas, so T exhaust, minus the T of the fresh charge, which is basically the air which was admitted into the cylinder through the inlet manifold. So we can say, okay, in, and then this is out. When you do that calculation, you arrive at this. Now, the heat to surroundings per minute is equal to 9 megajoules per minute minus the sum of all the other heat energies. This was to useful work, this was to cooling water, and then this was to exhaust. When we add them up and then subtract it from the total energy that was produced as a result of burning of the fuel, then we'll arrive at this figure, which is 0.9 megajoules per minute. Now, we were asked as well to express the items as percentages of heat supplied to the engine. So these just basic calculations. To do that, we just take the heat to useful work, which is 2.7 megajoules per minute, over the total, which was 9 megajoules per minute, the total of heat energy produced. This was to useful work. Multiplying by 100, then we get 30%. We do it for the others as well. Then we can be able to draw up our heat balance sheet. And it will look like this. So we have here heat to useful work, heat to cooling water, heat to the surroundings, heat to exhaust gases, and then heat to the surroundings. The heat that was produced from the fuel was 9 megajoules per minute, and that was like 100% of the heat that was in the engine. Then we got 30% to useful work. So 30% of the total heat was to work. That's what we will record at the output shaft of the engine. That is the brake power. So only 30% of the total heat energy that was derived from the fuel was able to be used to do work. Then the rest, which is basically a lot, goes to waste. So this can tell you in your mind's eye how much energy we are just throwing away. That is why technologies such as turbocharging, using the exhaust gas to do heating in the cabin. So you remember in your HVAC studies, heating, ventilation, and then air conditioning studies, you remember that like we can pass exhaust gas through some heat exchangers, which will now allow you to receive some amount of heating. I mean, for temperate regions where there is snowing, and then you just want to use the heat energy to, you know, de-ice your screens and then mirrors. So defrost your screens and mirrors. So we can use the cooling water heat or the exhaust gas heat to be able to do that. And many more other technologies are, you know, in effect in an attempt to just try to make use of this heat so that it doesn't go to waste. That is all for heat balance.